In this video, I'm going to give you a super easy and a very intuitive explanation of logistic regression. Logistic regression is a very fundamental and foundational machine learning algorithm. It is the backbone of any other classification models and also a key concept to understand if you want to learn deep learning. Most tutorials out there for logistic regression, they are very math heavy and do not give a very intuitive explanation of the algorithm. So in this video, I'll try to take a real life example and I'll try to explain to you that how you can use logistic regression to solve problems like these. And I'll try to use the minimal amount of math to intuitively and clearly explain to you the concepts of logistic regression. And I'll also show you that how it is related and to some extent derived from linear regression, which I've covered in a previous video. If you haven't watched that video, do not worry because I'll give a brief recap of linear regression in this video. If you have watched that video or already know what linear regression is, feel free to skip the next 1 minute where I'll be giving a quick recap of linear regression just to make sure that we all are on the same page. For linear regression, we took an example of an ice cream man. And since he knew that there is a strong correlation between that maximum temperature of the day and the ice cream sales he saw, he wanted to quantify that relationship. So when we looked at this data for maximum temperature of the day and the ice cream sales, we saw that there is a strong correlation. For days when the temperature was low, for example, 19 or 22, we saw that the ice cream sales were also lower. But on the days when the temperature was high, for example, 33 and 35, we saw that the ice cream sales were also high. So we wanted to quantify that relationship so that for the new day, he could easily calculate what the estimated number of sales would be. And for that, we plotted the ice cream sales versus the temperature, and we saw a trend emerging like this. So clearly there is a relationship between temperature and ice cream sales. And in order to make that relationship concrete, we drew a trend line through it using something like this. And this trend line was very powerful because for each new day, he could say that, for example, if see that the temperature is here, let's say 35 here, he could see that what would be the equivalent number of sales for that, and that will be his prediction. But the problem with this approach was that as we look at the data, there are more than one possible trend lines. So this is a trend line we draw, but we could have easily draw a trend line like this, or we could have easily draw a trend line like this. So there are multiple possible trend lines. So we wanted to know how can we find the line of best fit. And for that, we looked at the errors. An error is the difference between the line and the point. We saw that this is the difference. So this is error. And we saw this is the difference, this is the difference. So these are all differences, which is the gap between the prediction line and the data point. In an ideal world, there should be no gap. The line should be going through all the data points and there should be no gap between those. And that will be a zero error scenario. But in most cases, we see that there is a gap. So we wanted to quantify that gap. So we started looking at the gap between the actual data point and the prediction line. And then we tried to sum it up. But there was one problem. The lines which were above the data point, they were showing positive error. And the lines which were below the data point, the error was showing up to be negative because we are taking this point and then subtracting the line. Now, in order to overcome that, we took the absolute values of the differences. And that gave us the value of mean absolute error. So this is the error we are calculating, and we are taking the absolute values of these. And then at the end, we take the mean value, which is just an average. So this gives us a concrete way of calculating the error. Now, though this is a very valid way to estimate the error, there is even a slightly better way in which you basically take the square of the error instead of taking absolute value. So that is MSE, where S stands for square. And the reason this is better is because when you take a square of any number, it becomes positive, even if it is negative in the beginning. And also the square of large numbers is even larger. So it penalizes the large errors even more. Then we saw that how we can use libraries like scikit-learn to very quickly and effortlessly calculate all these things within seconds with just a bunch of lines of code. And nowadays, when ChatGPT and Google Gemini is there, you can ask it to create the code for these predictions and it'll do the work for you. So you don't even have to write the code. And finally, we saw that though these mean absolute error and mean square error values are good. The problem with these is that, let's say for any data point, I run this algorithm and I get the mean square error value of, let's say, 720. Now, I don't know if 720 is a good value or a bad value. So ideally we wanted a score value which is very intuitive to understand by just looking at the value. The difference is the same as, for example, if I tell you that in some math exam, I got 800 marks. Now, you don't know if 800 marks are good or bad. But if I tell you that I've got 89% marks, now you can tell that these are good numbers. So in order to do the same thing here, scientists came up with a measure of R squared. And that is basically a comparison of how good this prediction line is compared to if you had just calculated the average line across all these data points. So R square value tells you that compared to the average value of your data points, how good your prediction is. So this is a very quick recap of linear regression. If you still need help with that, go watch the previous video. And if you are still with me, let's look at the logistic regression now and see that how it builds on top of this knowledge to help us solve even other slightly different problems. To understand logistic regression, let's look at a different data. Let us say we are trying to estimate if someone has high blood pressure or not based on their body weight. And after taking some measurements, let's say we get a data like this. We can see that there is a trend for people who are low on weight, for example, 75 and 82 and 81, we can see that most of them do not have a blood pressure. But for people who are high on weight, for example, 138 kgs, they do have high blood pressure. So we know there is a trend line, we know there is a correlation, and high weight leads to high blood pressure. Now, trying to do the same exercise as we did for linear regression, let's try to plot these lines on a graph. But we have one problem. The problem is that to plot anything on a graph, we need to have numerical values, where here we have no's and yeses. Now, a very quick way to do it is that we treat anything which has a value of no equal to 0, and anything where we see it is yes, we take it as 1. By doing this, we can represent this data in a numerical form, and then we can do all the fancy math on top of it. So let's try to plot it on a graph. So this is our x-axis where we have the weight in the kgs. And for our y-axis, we just have two values, which is 0, representing no blood pressure, and then 1, which representing high blood pressure. And now let's plot all these data points on our graph. So now once we have drawn all these data points, which tries to either go through all the data points, which is clearly not possible here. So at least we can try to create a line which has the minimal amount of distance from the data points. So let's say by looking at this data, we got a trend line which looks like this. Now let's see if we can use this line to estimate if for a new person, given their body weight, we can tell if they have high blood pressure or not. So let's say a new person comes in with a very high weight. Let's say their weight is 140, and now we want to see if they have high blood pressure or not. So we can go up and see what's the value at this data point, which is, let's say, 1.8. Now, by looking at this number of 1.8, can we tell if this person has high blood pressure or not? We wanted to know if it is yes or no, if they have high blood pressure or not. But all we got out of this trend line is a value of 1.8. Now, how would we interpret it? Ideally, the output should be 0 or 1, so that we can tell if they have high blood pressure or not high blood pressure. So now one way to do it is that we clip the endings. So instead of going all this up, we just cancel this and we make the trend line like this. And we cancel all the negative values here and make the trend line like this. So now we have a new trend line which goes like this and this and this. Now let's see if we can use this trend line to give a prediction for a new person. Let's say a person comes up with a weight of about 100. Now what is the value of the trend line here? Let's say we go up and let's say this is 0.6. Now we wanted the values to be either 1 or 0, but we got a value of 0.6. How would we interpret it? Now, a very intuitive solution to this problem is that we, instead of taking the outcome as 1 or 0, we take the output as a probability or likelihood of someone belonging to that class. So in that case, we can see that 0.6 basically means 60% likelihood of someone having high BP. Now helps us solve a problem because we are getting probability distribution as an output rather than a binary yes or no. And this is even more useful than just getting a binary yes or no, because it gives us a likelihood of someone belonging to that class rather than just 1 and 0, and then we can adjust the threshold for cases where we want to be more sensitive to 0 outcomes or 1 outcomes. And the way we try to mathematically do this is by using a sigmoid function. It is a mathematical function which goes like this, where y is equal to 1 over 1. And the beauty of this function is that whatever value of x you pass it on into this, it stays between 0 and 1. The other benefit of using this sigmoid function is that it even makes this curve more smooth. So the sigmoid function output becomes something like this. It is even more smooth between the transition from 1 and 0. And another benefit of this, which you would later understand why it's a benefit, is that instead it asymptotes towards 1 and 0. What it means is that it stays very near to 1 as we go towards positive infinity, and it goes very near to 0 as we move towards negative infinity, but it never becomes fully 0 and it never becomes fully 1. Why it's a benefit, you'll see it shortly. So because of all these benefits, we use sigmoid function to estimate this trend line. Now, as we have come up with a solution on how we can use a trend line, which is not a straight line, but instead a sigmoid line, through this to find the approximation for a new data point. But it leads to another problem, which we also ran when we were doing linear regression, which is when you look at this data, there are actually many lines which are possible. For example, there is a new line which could go like this. There is also a new possible line which could go like this. So out of all these lines, which are green, blue, red, and could be many more, how would we know that which line best fits this data? And the way scientists solve that problem by using a function which is called maximum likelihood estimation. And this maximum likelihood estimation is a very important concept to understand, because it does not just get used in logistic regression, but has a lot of other use cases. It is also a very important question which gets asked for the interviews for machine learning roles. And it is slightly difficult to understand. Most of the explanations which you see out there are just explaining the math of it. So you can definitely memorize all those equations, but I bet you that even if you ask experienced data scientists out there, 90% of them would not be able to clearly and intuitively explain to you what is maximum likelihood estimation. So in this video, I'll try to keep the math low, and I'll try to give you a very intuitive and hopefully very easy to understand explanation of what is maximum likelihood estimation. Maximum likelihood estimation is actually very similar to the way we calculated mean absolute error or mean square error in the linear regression line. And the fundamental concept there is that we try to estimate that what is the error or distance between this trend line and this data points which we are observing. Now, the problem with the logistic regression is that our trend line, which is this sigmoid line in this case, it represents likelihood of someone belonging to that class. So we have to change the way we think about errors instead of just absolute difference to what is the difference in likelihood. Now, to easily understand maximum likelihood estimation, let me again draw the plot we were talking about. So on y-axis, if someone has high blood pressure or not, x-axis indicates their weight in kgs, and it started from 80 and went all the way to 140. And then on the y-axis, we just had two outcomes. One is 0, which is no high blood pressure, and then there is 1, which is they have high blood pressure. Now the data point distribution we saw was something like this. Most people who were on the lower side of the weight did not have blood pressure, and most people who had on the higher side of the weight did had high blood pressure. But then there were some people who had low weight but still had blood pressure, and some who had high weight but still did not have blood pressure. So there was a little bit of anomaly in the data. And then let's see if there are some people here. Cool. So in the previous step, based on this data, we draw a sigmoid function which went something like this, and realize that this asymptotes towards 1 here but does not really touches 1, and this asymptotes towards 0 but never really touches 0. Now let's see how we can calculate the maximum likelihood estimation for this line. So basically what maximum likelihood estimation says is that if we know that this line is true, then what is the likelihood of us seeing these data points? So if this line is true, then what is the likelihood of us seeing these data points? Now let me explain what does it mean. To do the actual calculation of maximum likelihood estimation, we have to look at each of these data points, and then we have to see if this trend line is actually true, then what is the likelihood we would see this data point. So in this case, we can see that if someone, let's say, have a weight of 140, if this probability distribution is correct, then what is the likelihood of us seeing this data point? So in this case, it is almost 100%. It is 99.999%, but we can say that it is actually 100%. Because if this is actually the trend line, then if someone has a weight of 140, this matches here. It means that the value of this line here is about 0.99, which means 99.99% probability or likelihoodness. Same goes for this line. It is again 99.99. For brevity's sake, I'll just say 100%. For this one, it is not 100%. It is slightly lower than that because the line has not reached almost 100. So let's say I'll say 80% for this one. For this one, it is even lower. So let's say 70%. And for this one, it'll be about 0% because if this is the actual trend line, then someone having a weight of 82, their probability of having high blood pressure should be very low, as we can see. So it will be about 0.001%. And then we do the same exercise for these points. What is the probability of someone having no blood pressure if this trend line is true? And as we can see, it is almost reaching 1. So their likelihood of not having a blood pressure would again be very, very low because it is almost reached 1 here. So it will be 0.001%. And then what is the likelihood of someone not having a blood pressure if they have a weight of somewhere here? Let's say if it is 95. We can see that intersects here. So the probability of not having blood pressure would be somewhere around, I'll say 40% based on this. What is the probability distribution of someone like this? It will be around 10%. And here it will be almost 100%. So for someone having this blood pressure, it will be about 90%. For someone like this, almost 100%. And again, almost 100%. Now, once we have the probabilities or likelihoodness estimated for each of the data point, if we know that this trend line is correct, then the next step is very easy. We just multiply all of them, and that gives us the maximum likelihood estimation. So let's say we multiply these, all of them, and we get a number which is, let's say, 0.04, which will be our maximum likelihood estimation. So this will tell us that how good or bad this trend line is. Ideally, this trend line should be closer to 1 because if we see everything is 99.9, 99.9 and almost 100%, then when we multiply all of them, it will again be 100%. So if the product of all of these is, let's say, 0.01, then to calculate MLE, we just have to take a log of it, log of this value, and then through maximum likelihood estimation, we try to maximize this value. So whenever we are comparing two such trend lines, we can calculate the maximum likelihood estimation for each of these lines, and then we can see what is the value. And whatever gives us the most value, that is the line of best fit. And that is what we finally use to make the rest of the predictions. Now, as you can see, it is a lot of work to do manually. Luckily, we do have help of computers to help us solve problems like these. So let me quickly show you that how you can use Python library scikit-learn to quickly train your own logistic regression estimator given these data points, and then how you can use them to make a prediction on any new data point. So this is how you initiate this model and then fit it on the training model. X here represents the independent variable, which for our example was the weight of the person, and then Y represents the dependent variable, which in our case was if they have high blood pressure or no. and it is represented in zeros and one. One indicate they have high blood pressure and zero indicate they do not have high blood pressure. And within a couple of milliseconds, the model would be trained. Now you can use this to make predictions on the new data points. Let's say if I want to know that if this new person with this body weight, they have the blood pressure or not, I can just use this command of classifier.predict and pass on the weight, and right there it tells me if they have high blood pressure or not. Another very useful feature is that you can not only get the value of 1 or 0, since the model has calculated this sigma line which we have represented here, you can actually use this to get the probability of someone belonging to the class of if they have high blood pressure or not. So the syntax slightly differs. Now you'll say classifier.predict_proba and then pass on the weight, and then it will tell you the probability of someone belonging to that class. And just like logistic regression, you can pass on as many weights as you want and it will tell you if all those people would have blood pressure or not. And by using the predict proba command, you can also see what would be the probability of someone having a blood pressure in all the data points you have passed it. And if you want to know how well your model is doing on some test data, you can just pass in the test X and test Y. It will give you the score of that model. Now the score which it gives is that of accuracy. Now accuracy is not always a very good measure to score a classifier. For example, let's say if you're trying to detect a fraud in a banking transaction and you have trained a classifier for that. Let's see, for every 1 million transactions, there is just one fraudulent transaction. Now let's say if you just train a very dummy classifier which predicts no fraud for every single transaction you pass in, that dummy classifier would be right 1 million times when there is actually no problem in the transaction. But the one transaction which has the fraud occurring, your model will even for that say that there is no fraud. Now when you calculate the accuracy of this model, it will be 0.999999%. Now, of course, on paper it looks good, but that model is useless because no matter what transaction you pass it on, it will always say that it is not a fraudulent transaction. So when we have this kind of imbalanced data set, then accuracy doesn't truly represent what we care about. Another word of caution I want to make here is that when you use the .predict command in this classifier, it by default takes 0.5 probability as a threshold. Anything below 0.5, let's say 0.3 or 0.4, it classifies at 0. Anything above 0.5, let's say 0.6 and 7, it classifies at 1. Now this works for a lot of use cases, but again, going back to the example of if you're trying to find the fraudulent activity on credit card transactions, and let's say based on this classifier, you're trying to build a system which notifies you if there is a probability of someone misusing the credit card. Now, if your system only alerts you when the probability is 0.5, then that is actually dangerous. You want your system to alert you even if the probability of fraud is 0.1% or even lower. Now, to fully explain these two questions, first, if accuracy is not the right measure, how else you can score and evaluate different classifiers? And second, if 0.5 is not always the right threshold, then what is the good way to calculate what should be the right threshold? In this video, I've explained all the good stuff. How do you calculate confusion metrics? What is precision? What is recall? What is F1 score? Why and how do you calculate area under the curve of ROC curve? So please check it out. I'm pretty sure you'll like it. Thank you so much for watching.